Hi, this is John Whitaker for the Mathematical Analysis 2 class. This is our 32nd video lecture and our last video lecture. We're going to prove three things today and talk about a few new definitions, and then end the class with the statement of the Stone-Weierstrass theorem, which we won't prove. The first thing that we're going to talk about is a corollary to the Weierstrass theorem. And if you remember, the Weierstrass theorem had to do with any continuous function, complex value function, can be approximated by uniform convergence of polynomial functions. Well, here's a corollary to that. So the corollary is for every interval minus a to a, there exists a sequence of polynomials P sub n such that P sub n of 0 equals to 0, and the limit as n goes to infinity of P sub n of x is equal to the absolute value of x. And this is uniform on A to B. Sorry, minus A to A. We're going to prove this seems a little bit out of focus. I think it's back in focus now. Here's the proof. It's by the Weierstrass theorem. There exists a sequence of real polynomials I'll call them P sub n star, which converge to the absolute value of x uniformly on minus a to a. Note the limit as n goes to infinity of these P sub n star of 0. So that's a sequence of numbers. That's equal to 0. So the sequence of polynomials P sub n where P sub n of x is equal to P sub n star of x minus P sub n star of 0. That sequence converges uniformly to the absolute value of x on a to b, I'm sorry, minus a, whoops. So that sequence, the piece of n's, converges uniformly to the absolute value of x on minus a to b, divided a. And piece of n of 0 will be equal to 0. So that ends that proof. Now we're going to look at a series of definitions. First, we're going to start off with an algebra. A family, strip A, of complex functions defined on a set E is called an algebra if three things are satisfied. And those three things are I should write it this way. If for every F and G element of script A, then 1, F plus G is an element of script A. 2, F times G is an element of script A. And 3, C times F is an element of script A, where C is a complex number. We can similarly define an algebra for real functions. They have the same three properties with C being an element of R as we have a complex. Okay, so if you add two guys from the set, or two guys from the family, you're back in the family. Multiply two guys from the family, you're in the family. And if you take a constant times a member of the family, you're back in the family of functions. Well, another definition is that of an algebra being uniformly closed. Here's what it says. It says, let script A be an algebra. Suppose for all sequences of functions F sub n that's a subset of A, so these are sequence of functions contained in A, that converge uniformly to, let's say, some function F, then F is in, I should have written this A little better, A, Then A is said to be uniformly closed. So that's what it means for algebra to be uniformly closed. It means all the uniformly convergent sequences of functions, limits functions, are contained in A. Another definition is we let A be an algebra. Let script B be the set of all limits, all functions, which are limits of uniformly convergent sequences of A. Then B, is called the uniform closure of A. We'll look at an example next. So, as an example, if you let script A be the set of all polynomials on the closed interval from A to B, this is an algebra. Two polynomials together, you get a polynomial, multiply two polynomials together, you get a polynomial, multiply a polynomial by a constant, you get a polynomial. Because of the Weierstrass theorem, really, I'm going to start calling this the Weierstrass approximation theorem. Then the uniform closure of A is script B the set of all continuous functions on A to B. So those are the limit points, the limit functions, uniformly convergent sequences in polynomials. Next, we have a theorem that we're going to prove. It states, let B, script B, be the uniform closure of an algebra script A of bounded functions. Okay. Then script B is a uniformly closed algebra. So we got to show that script B is an algebra, and then we also have to show that it contains all of its limit functions. Okay, let's work on that proof. So we're going to let script B be the uniform closure of an algebra of bounded functions. We want to show B is an algebra that's uniformly closed. Okay. So we let F and G be an element of script B. So what is script B? Script B was the a uniform closure of script A. What does that mean for it to be the uniform closure? It means that it's the limit functions. And so what that means, thus, there exists a sequence of functions so there exist sequences, I'll say. F sub n running from 1 to infinity, is a subset of script A, and with F sub n converging uniformly to F, and a sequence G sub n, that's a subset of script A with G sub n converging uniformly to G. Okay. Now, F sub n plus G sub n, that will be a sequence in A, because A is an algebra, so if F's in A and G's in A, F sub n's in A and G sub n's in A. When you add them, you get something in A, so this is a sequence. This in A. Where F sub n plus G sub n converges uniformly to F G. Okay. F plus G. I'm not putting in the details here. I've asked a homework problem similar to this, and so I'm not going to put any more details. I'm going to have you do the homework problem. It had to do with subtraction. So that says F plus G is an element of script B because it's the uniform closure of A. Okay? Now, since F sub n and G sub n are bounded by a homework problem I'm giving you, then F sub n times G sub n converge to F times G uniformly. Okay. I'm not putting in the details here, but let me just say that F sub n is in script A and G sub n is in script A, and because script A is an algebra, this multiplication is going to be in script A. The boundedness gives the convergence to F of G. And so F times G is a limit of a sequence in script A, so that means F times G is an element of script B. Okay. Now, lastly, show that we have an algebra. We're going to let C be a complex number. We want to show CF is an element of script B. Okay. And the way we will do that is the following. We will show CF sub n converges uniformly to CF.
first case, if you will, is if C equals to 0, then you look at this function C f of n. That's the function. It is in the algebra script A, but it's the sequence of functions. It's always 0, which converges to 0, that function, uniformly. So CFN converges uniformly. In this case, C times F, which is what the 0 function will be if C is always 0. Okay? Now, if we'll suppose C is different from 0, and we're going to let epsilon be greater than 0 be given. So I'm going to use the definition of uniformly convergent. We need a natural number script n such that for all n bigger than or equal to script n, C times f sub n of x minus C times f of x will be less than epsilon, and that's true for all x in our domain, which I think I labeled Z. Okay. We know that C times f of n of x minus C times f of x is equal to the absolute value of C times f sub n of x minus f of x. Okay. Since the f sub n's converge to f uniformly, then there does exist a natural number n number. So this is using the definition of uniformly convergent, such that for all n bigger than or equal to this big N, the distance from f sub n of x minus f of x, that's going to be less than anything that I want. And so I'm going to pick epsilon over the absolute value of C. So for all n bigger than or equal to this big N, wait a minute, I'll insert something. And this is true for all x element of E. So for all n bigger than or equal to this big N, we have the distance between C sub f sub n minus C sub f, oops, I better put x here, which is equal to the absolute value of C and f sub n of x minus f of x. This guy can be replaced by epsilon over the absolute value of C, and he got smaller. So here's the absolute value of C times epsilon over the absolute value of C, which is equal to epsilon. Thus, C times f of n converges uniformly C times F. Thus, let me write a conclusionary statement about that. That's going to tell us that C times F is in D. So what does that tell us? That tells us that strip D is an algebra as it satisfies the three qualities to be an algebra. We want to show that B is uniformly closed, okay? So now, here's the way we're going to do that. The first thing is if we let F sub n if we let F be an element of script A, then the sequence F sub n, which is always just the function F, so it's a sequence of the same functions, then that converges uniformly to F. So that says that F is an element of B, as this F is the limit of a sequence of functions that converge uniformly to it. And so that's what it means to be in B, uniform closure of A. And so that says that script A is a subset of script B. Now, next thing, and I'm not going to go through all the details here, the sup norm defines a metric we have a homework assignment system that will define a metric on C of X, but it really defines a metric on the collection of complex value functions. So script A is a subset of this metric space. Is a subset of this metric space. The metric space is the collection of all complex valued functions defined on D with the sup norm metric. Okay. Where convergence occurs, okay, if and only if F sub n subset of A, so this is a sequence in script A. It's a sequence in in this metric, I should say, converges uniformly, okay, on E. So, what we have is that B will be equal to a closure in this metric, okay? Okay. Thus, B is closed in this metric space. And that's because the closure of any set is a closed set in the metric space it belongs. Thus, B contains all of its limit points. Thus, script D is uniformly closed. That ends that proof. Okay, ladies and gentlemen, we've got two more definitions, theorem, maybe some examples. One more theorem that we won't prove to go. Here's the next two definitions. We let script A be a family of functions. On then script A is said to separate points on E. If to every pair of points of distinct points of E, say x sub 1 and x sub 2, there exists a function f that's in A with f of x sub 1 being different than f of x sub 2. Another definition is we let script A be a family of functions on a set E if to each x in E there exists, or there corresponds, a function g in A such that g of x is different from 0, then script A vanishes at no point of E. That's what I'm defining. What does it mean for script A to vanish at no point of E? Okay, we want to look at an example. Let script A be the set of polynomials on R, then script A separates points. What does it mean, separate point? That means for every real number, there's some function out there, every pairs of real numbers that are not the same. There's some function out there such that f of those two numbers are the same. And so, as f of x equaling to x, that's a polynomial, is an element of script A, and if x of 1 is different than x of 2, f of x of 1 will be different than f of x of 2. Also, script A vanishes at no point of R as for x being different from 0, f of x equaling to x is different from 0, and for x equaling to 0, g of x equaling to x plus 1 is going to be different than 0. I'll just say it. I'll say it this way. The property g of 0 is equal to 1, which is different from 0. That's right. Let's look at another example. The set of all even polynomials these real polynomials on minus 1 to 1 does not separate points. And the reason it doesn't separate points, as you give me some polynomial that's even, then f of 1/2 will be equal to f of minus 1/2. Remember, even means it's symmetric about the y-axis. Okay? Those will be the same. For every even Okay. Want to write up the theorem, prove it, and then give the Stone-Weierstrass theorem. Okay, so here's our theorem. Suppose script A is an algebra of functions. So it's an algebra on a set E. A separate points on E, and A vanishes at no point of E. Suppose x sub 1 and x sub 2 are distinct points of E. And C1 and C2 are constants. Then A contains a function we're going to call it F, such that f of x sub 1 equals to c sub 1, and f of x sub 2 is equal to c sub 2. No matter what x sub 1 is and x sub 2 is, and what c sub 1 is and c sub 2 is, I can find such a function in this algebra. And we're going to create that function in general terms. So here's the proof. Since script A separates points on E, there exists a G, element of A, with G of x1 being different than G of x2. Since script A vanishes at no point of E, there exists functions h and k in A such that h of x sub 1 is not 0 and k of x sub 2 is different from 0. Okay, we're going to define two functions now. We're going to let u be equal to g times k minus g of x sub 1 times k, and v be equal to g times h minus g times x sub 2 times h. That's our functions. I'm gonna write this down, but what we're gonna see is G and K were in A, it's an algebra, so that multiplication's in the algebra. Here, this is a constant. You think of it as negative quantity here, we're gonna say it's minus, or apply the minus to this number here. And that's a constant times K, so that's gonna be an algebra. When you add them together, you get something in algebra. And the same thing here. So U and V are in A. Okay, so let me write that down. Note, U and V are both elements of this algebra. Also, U of x1. Okay, that's going to be equal to G of x1 times K of x1 minus G of x1 times K of x1, and of course that's equal to 0. And V of x2 is going to be equal to G of x2 times H of x2 minus G of x2 times H of x2. Of course, that's the same thing, so that's equal to 0. Okay. Now, look at U of x2. Now, U of x2, by definition, is G of x2 times K of x2 minus G of x1 times K of x2. And that's equal to, well, it's K of x2 times G of x2 minus G of x1. Sorry. Now, one of the things about K was it was the function that doesn't vanish at x of 2. So what I want to tell you is, by definition of K, how we get K, this is non-zero. This right here, G of x2, is different than G of x1. That's how we pick G. So we got two non-zero numbers being multiplied together. That can't be 0. So U of x2 is not 0. Finally, V of x1, what V of x1 is equal to is G of x1 times H of x1 minus G of x2 times H of x1, which is equal to H of x1 times G of x1 minus G of x2. And again, that's non-zero because H of x1 is not 0 and these two guys aren't the same. Sorry. We're almost done. we define is c sub 1 over b of x1, which we know is not 0, times b of x, plus c sub 2, u of x2 over u of x. I'm sorry, times u of x. Okay, now note, f of x1 that's equal to c1 over b of x1 times b of x1, which will cancel, plus c2 times u of x2 times u of x1. Well, one of the things I think we had about u of x1 was that it was 0. So this part is 0. These two things cancel. That's equal to c sub 1. Also, f of x2, that's equal to c1 over b of x1 times b of x2 plus c2 over u of x2 times u of x2. All right, these two guys cancel, so we're just left with c sub 2. b of x2, that's equal to 0, so this part is 0, so we just get c sub 2. We have just created the function. And f is in, I need to say this. I didn't say this. Where f is in A. And why is f in A? Because it's an algebra. Look, v is in A, u's in A. These are constants times these functions, so each one of these quantities are in A. You add them together, because A is an algebra, you get something in that. That concludes the verb. Lastly, I'm going to stay here. It's called the Stone-Weierstrass theorem. Here's what it says. It says let A be an algebra of real functions real continuous functions. Sorry. On a compact set, okay, if A separates points on K, and A vanishes at no point of K, then the uniform closure, which I'll denote in B, of A, consists of all real functions real continuous functions on K. Well, ladies and gentlemen, that's the last thing I wanted to state. Please be aware of the stone fire stress theorem. And thank you very much for your time and patience. That concludes the material for this class.